This is Lab 2 for Physics 2211, which looks at the physics behind the motion of a falling object. The purpose of this lab was to observe the motion of a falling object that has dropped from rest and falls slowly straight down, and to compare the observational data to a computational model based on the momentum principle and another computational model based on the momentum principle that considers the effects of gravity and drag. The results found that the computational model that included the effects of drag force predicted the position of the object more accurately than just the weight force alone. The physics principles behind the lab are Newton's second law and drag. Newton's second law, is seen in the form below, is derived from the momentum principle, where the final velocity is equal to the initial velocity plus the net force divided by mass times the change in time. In this experiment, the velocity is not constant because the net force is non-zero. We have two forces acting on the object, the gravitational force and the drag force. The velocity is then used in the position update equation to update the position of the fallen object. This then repeats with the final velocity being used as the initial velocity and the final position being used at the initial position to iterate through the second set period of time. The net force is calculated by adding together all the forces acting on the object. In this case, that would be the gravitational force, also known as weight, and the drag force. The gravitational force is found by multiplying the mass of the object by the gravitational constant times j hat. The drag force is the force acting on the object in the opposite direction to its velocity. It's found by multiplying proportionality constant b by the square of the velocity. The experimental setup is as follows. The mass of the ball was 0.0023 kilograms. We used a reference length of 0.121 meters. The frame rate we recorded with was 30 FPS. We oriented our axis in the upwards direction where it's in the positive y direction. And our initial position and initial velocity were both the zero vector since the ball started at rest. Here's a video of our observational data. As you can see here, the observational data was tracked with the tracker software. The graph demonstrates that the time versus y position of the falling object. The object is not moving with a constant velocity, which is why the graph curves rather than being a straight line. This is my Python code for just the weight force acting on the ball. The ball's mass was updated as well as the position and velocity vectors made to be 0. The time step was chosen to set a small number to the data so it will be analyzed to be more precise. The j hat vector reflected the axis chosen, which is the y-axis. The time was updated to match the length of the video I recorded. The calculation for the weight force was added in as well. With just the weight, we put in that F net equals W in the code. The velocity equation and the position equation were updated to reflect Newton's second law. After the code was run, the results look like this. When we compare the observational data to the computer model of the gravitational force acting on the ball, we get a graph as shown below. As you can see, the model overestimates the effect of the gravitational force on the object. It is inaccurate because there are two forces acting on the ball other than just weight. The other is just the drag force. The unevenness of the observational data could be a result of movement in the x direction, which hints that the ball did not fall completely straight down. With drag force added in, the model will behave like the observational data. This is my Python code for the combined forces of the weight and drag on the ball. In this case, everything was kept the same except for the proportionality constant, which was found by a process of trial and error by changing the constant until the output y position model was matched to the output y position of the observational data. Then in the while loop, the code was updated to reflect the drag force, which is negative b times the magnitude of velocity squared times negative j hat. The net force was updated to where it included both weight and drag force in its calculations. The last changes were in the bottom part of the code. We want to represent the forces with arrows. The arrow scale was defined by dividing 2 meters by the magnitude of the gravitational force to determine how long to draw the arrows to represent the vectors. This is the result from the Python code. The last bit of data analysis compares both models to the observational data. As you can see here, that the model predicts the position using both weight and drag is much more accurate than the model that predicts the position using just weight. However, we use our observational data to fit the drag model, so the final position isn't actually a predicted position. And so the middle of the graph from approximately 0.1 seconds to 0.6 seconds is a predicted output, and this measures that the drag model still overpredicted the position. Overall, the model that included both drag and weight forces is the best predictor of the object's position. Now, to answer the first question, the drag force model predicts terminal velocity. Terminal velocity is at a certain speed, the drag force is equal to the gravitational force on the object, and the object no longer accelerates, leading to it falling at a constant speed. This can be seen in the graph below at approximately 0.6 seconds. The object's position is changing at a constant rate, which indicates that there is a constant velocity, meaning the object reaches terminal velocity in this model shown by the red square in the graph. To answer the second question, if the object was thrown with an initial velocity, the terminal velocity would occur faster than if the object was dropped from rest. The head of the arrow showed that the object begins to move at a constant rate, and this is earlier than if the ball was dropped at rest. The object would also be predicted to drop further.